So first of all, let us understand our data set, what kind of data set we have. And classification will be a very long discussion because there are a lot of different types of use cases that we will talk about. So first, we will start with some academic examples just to build the foundations in terms of what is classification. And as we are able to understand the different concepts and the different ideas of classification, so from there we'll enter into some very, very real world use cases in terms of how classification is done. Okay, so this is the data set that we are taking up right now. We're looking at the different features of a particular person, and based on the different features of a person, we are trying to predict whether a person is diabetic or not. Okay, so you can see predict the onset of diabetes based on diagnostic measures. Okay, and also we are seeing a rapid amount of progress happening, especially in this field of in this specific field. We are seeing a lot of companies and especially a lot of healthcare companies, a lot of health startups are uh, jumping on the bandwagon where they are, they are looking at your health history, they're looking at your diagnostic test results, and based on all the different parameters, these companies are trying to predict. Okay, so based on all the different parameters, these companies are effectively, are trying to predict whether you will have a particular disease or not. Okay, so it's a very real, use case that we are talking about. Okay, so it could be diabetes, it could be cancer, it could be other kinds of diseases. Okay, a lot of these kinds of models were used during COVID, right? So how you can take preventive action, you can identify based on certain types of symptoms whether a person is likely to have COVID or not. So again, if you think about it, they're all classification problems. So based on a set of features, based on a set of attributes, you're trying to predict whether a person has a medical condition or a person does not have a medical condition. Okay, so that's the thing that we are trying to solve. These are some of the features we have. Do not need to memorize all this in detail, but just to get an idea so that we relate to, we understand what we are trying to solve here. So every row stands for a person, and we have the different features of the person. So you can see that uh, it stands for the number of pregnancies, the amount of plasma glucose in the bloodstream, the blood pressure of the person, the skin thickness, the insulin level, the body mass index, uh, the insulin level, the body mass index, the diabetes pedigree function, and the age. So these are the 8 different features of a person. And based on the 8 different features of the person, we are trying to predict what is the class. Okay, so I repeat again, based on the 8 different features of the person, we are trying to predict what is the class. Okay, if the class is 1, that means the person has diabetes. And if the class is 0, the person does not have diabetes. Okay, class 1 means person has diabetes, and class equal to 0 means person does not have diabetes. That's the problem that we are trying to solve here overall. Okay, so now let's move on. Let's come to the actual solutioning. Okay, this is the thing. All of you can see. So initial part is very straightforward. We are loading the libraries and we are using. So in many times in my code, I just want to clarify one thing. Many times in my code, you will see this command called drive.mount G drive. You don't need this. I already clarified this yesterday. You do not need this. In case you come across this particular syntax, you can safely ignore it. All that this will do is it will load my Google Drive on my collab. Okay, if you want to see, I'll run this for you for a minute. I'll show you what I mean to say. So if I run this code, you will see after a while when I mount it, this G drive will be available in my collab, in my working directory in collab. This is what will happen. So, but you don't have to do it, okay? It will ask me to, I have to give it permissions to, connect my notebook to my Google Drive. I'll say connect to Google Drive and I have to sign into my account now. Continue. You have to give access to all these 9 services, which I already did before. So, but if you get some check boxes, just make sure to check everything. And once you do that, this drive will be available in my working directory. And I should be able to access all the files from my Google Drive. That is the concept. So no such directory because that directory does not exist right now, but that's okay. That's not that important right now. But you can see, I think, yeah, Outlook.com is the same folder, but I think this is the different path. I can modify the path, and if I modify the path right, it'll be fine. If you want to know how to do it, I can show you. So this is my, again, if you just refresh, you'll see my uh, you know so if you see in the content, so I have mounted my G drive, and if you just go back to the previous directory, you will see that my G drive is mounted. Can you see? This is my G drive. Okay, so if I expand this folder, G drive, my drive, I should be able to access all the contents of my G drive, my drive. Okay, and I can copy the path, and that will work fine. And I think here the it is giving an error because I think the right thing is not set. So I can just go and make sure I type in the right thing. AI Gen AI training main. I can also copy path and show you that way. But let me show you this way. So AI space Gen AI training main. So AI space Gen AI. Gen is capital or small. Let me just see. Yeah, Gen AI training main. I'm just doing it in a very manual way, but you don't have to. Okay, so that's why I say it. I mean, you can absolutely do copy path and do it. And this is general machine learning training. This is fine, general machine learning training, and then diabetes detection case study. This is also fine, diabetes detection case study, and Pima Indian diabetes data. Okay, I think this looks okay. And if you see when I run this code now, it will be fine. So it's already mounted. Now it's taking the data from my G drive, my drive, and inside that I've got all these folders. I'm not showing that right now. This is my Google Drive space. I'm not showing it directly, but you can see that this is all present in my Google Drive right now. You all have the folders here. But you don't have to do it this way. Uh, if you're trying to run this at your end, you can simply upload the file and you can work it out. I already showed you a very easy way to work it out. Okay, if you think all this is too complex, then you can just directly upload the file. Just directly upload the file. You have an upload button, upload the file, and you can work with it, right? But this is also very helpful in a very practical situation. This is also very helpful in scenarios where you've got very big files. Maybe not in this session, but especially once you go to advanced computer vision, once you go to generative AI, you'll be working with very, very big data, let's say of the order of magnitude of hundreds of GBs worth of videos and audio data. So in that kind of a scenario, it is very difficult to uh, download and upload your data. Even if you try to upload your data into your session storage, it will take like hours to do it. But if you already have something saved in Google Drive, then you don't have to go through that manual process of downloading and uploading, because that's pretty much what we have to do, right? In these exercises also, if you remember, I'm sure you would have downloaded this. So first level you will download, next level you will upload, but that's a time consuming process. So instead, if you already have something saved in Google, you can mount your G Drive and you can directly connect from Google. Okay, so this is a much more dynamic solution that we have here. So I wanted to show you both the approaches. So whichever works for you, you can try it out. So we load the data into a data frame. Class is my output column. So nothing much to talk about. Is the same process that we have discussed before. Okay, this is the same process. One more very interesting concept I would like to discuss here is the idea of the pair plot. Okay, this is a very conceptual thing. If you see, we have the class, which is the output column, and this is the syntax how it looks like. We have sns.pairplot demo, diag kind equal to KDE. So the diagonal kind will be a smooth histogram. It's a KDE, which stands for a kernel density estimate. It's a smooth histogram, and hue equal to class. Okay, so I can run the code in a little bit and show you what I mean to say. Okay, so let me run the code. These parts are not that important. Okay, you can ignore these parts. All I try to do here is I try to identify variables, try to do a little bit of data pre-processing, error handling, because I mean, this is the part that will usually keep going on and on and on, because there is no end to exploratory analysis. Whenever you see any data set, there will always be problems, and that is exactly what I try to decipher and find here. So I actually found that uh, the pressure feature, the blood pressure feature, there are values which are zero. So for example, if you look at the minimum value for blood pressure, it's actually coming out to be zero, which is not possible. I mean, even for the other columns, if you see body mass index, blood pressure, glucose level, this is the like the typical glucose level in the bloodstream, plasma level, that is zero. It's not possible that a person's blood pressure is zero. A person's BMI is zero. It's not possible unless you are dead. I mean, it's not possible. So most likely this is wrong data. And this is again kind of error handling that we are doing. See, Python will not complain. If you try to take this data and build a model, no problem. Everything will work fine. You will get a working model, but the results that you get will be wrong. Okay, so that's why these are the kind of things that will take time. Getting a basic POC out of the way is very easy. You can take a data, you can do model.fit, and you get the scores and you can show it to your stakeholders. Fine, project completed. But the things that take time are these iterative approaches that we are making. That New York City case study that I showed you, experiment one, experiment two, experiment three. That's the thing that takes time. You break it into weeks, you break it into sprints if you're doing a agile methodology, and you complete different chunks of work in different sprints. These are the things that will actually take a lot of time usually. Okay. Anyways, so this is a bit of error handling that I'm doing. You can go over this later on. Now let's come to this. This is the very conceptual part now. Okay. SMS.pair plot demo direct kind equal to KDE, Q equal to class. By the way, what is KDE? If I do it a little differently, let's say instead if I use hist, what will happen? This is the default actually. So if you say hist, I will get normal histograms. This is something we can relate to. So all the diagonals will be like histograms. If you just see, let this run. Seaborn is a high level Python visualization library. That's what Seaborn actually is. So if you see, this is histogram. We can all relate to it. And we are breaking it by classes. Hue equal to class means color by class. Hue means color, right? Hue basically means color. So when I say hue equal to class, I'm basically saying, hey, color by class, color by the class column. That's the inference actually. Okay. So I'm treating histograms, but this is hard to see, right? I'm sure you can relate to me that uh, if you want to do a visual analysis and a comparative analysis, it's hard to see. So what you instead want to do, you want a smooth histogram. That is a KDE. So KDE stands for a kernel density estimate. Mathematically, it's a probability distribution. Okay, but in simple analogous terms, it's like a smooth histogram. Okay, you're approximating the histogram, you're smoothing the edges, think of it like a smooth a density estimate of a histogram. Okay, yeah, I'm skipping the mathematics. There's like, we can spend entire day and talk about KDE. So we need to get into like things like probability distributions, and this is a density. It's like a probability density estimate, and that itself is based on confidence interval. Some of you can relate to me if you're a bit aware of inferential stats. You can relate to what I'm talking about. So this entire thing is an estimate. So based on the actual frequencies of the histogram, so this is kind of a smoothing that we are doing. We're trying to estimate the exact edges of the histogram. Okay, so using confidence intervals, this is how it is actually created behind the scenes, but it's really not important if you're solving problems. If you This is what I meant, like this is the difference. Like, knowing the theory is useless. Now we can take the entire day and learn the theory, what is a KDE and how is it computed, but knowing that is useless, because when you're solving real problems, knowing what is a KDE will not help you. But yes, sometimes interviews ask you that question. Sometimes I really don't know why, why they do that, because my point is, if you're not applying a concept, then there is no point knowing it, right? What's the point in knowing something if you're not applying it? Okay, so yes, I mean, it's good to know, it's good to learn, it's good to be aware. Hey, I know what is KDE. It's good to feel great about it. But honestly, will you need to use it? Will you need to use that knowledge in real problems? Honestly, no. You just need to know how to use KDE. So oftentimes the usage is more important than just knowing the theory. What is it? Reading 2 pages of books and learning what is it? That's useless actually. Okay, let's understand how the KDE concept is getting used here. Let's see that. Okay, so if you remember, okay, another very interesting thing I want to show you is how you can kind of see this image in a different window. So right now you see the whole image. It's very hard to see, right? So what you can do is you can right click and say open a new tab. So the entire image will be rendered in the new tab. Okay, this is what this neat trick that all of you can use to see the complete picture. Okay, even within the Jupyter notebook, if you want to get a slightly zoomed in view, what you can do is you can actually kind of double click on the plot. See what I'm doing? I'm actually double clicking on the plot. You click on it once, you get a bigger picture. Click on it again, picture becomes normal. Click on it once, click on it again. Okay, these are some small neat tricks I wanted to share. Anyways, let's go back to the diagram. So what we have here is all the 8 different variables, and the colors basically stand for the classes, right? What are the classes we have, friends? We have 2 classes, if you remember. So I'll take a different color. So we have the class blue, which stands for not diabetes, and the class orange, which actually stands for diabetes, D. So the class orange stands for diabetes D, and the class blue stands for not diabetes ND. Now, what is the concept around it? What are we looking at here in this diagram? Let's see that. In this diagram, we are able to visualize the separation between the classes. There are 8 features, right? We have features starting from pregnancy, plasma, pressure, all the way up to age. So we have 8 different features in this particular data set, as we can see here. What we are able to see here is uh, the separation between the classes across all these features. So whatever features we have across all the features, we are able to understand how the classes are separated across all these features. How are the classes separated across all these features? That's what we are able to understand. Okay. So for example, if you look at the second feature, the one that I was highlighting, you can see the screen now better. If you see the second feature, this is the plasma feature. Remember, plasma stands for glucose. This is actually nothing but the glucose level. Glucose, how we measure glucometers, use glucometers in our homes to measure diabetes levels. So glucose level. So it's like a glucose level. Think of it that way. Okay. What it tells you is, and again, ignore the y-axis. The y-axis is like a frequency. The x-axis is the glucose level. This is the way you read the plot. The x-axis is the glucose level, and the y-axis is the frequency. Maybe if I show you in a better way. So this is the glucose level, GLU. This is a distribution plot for not diabetes. So you can see for all the not diabetic people, what are the average glucose levels? And this is showing you the distribution plots for all the people who have diabetes, D. And you can clearly make out, so I've just drawn this diagram in a bigger way here. You can clearly make out that people who are diabetic on an average have higher glucose levels. That is the interesting part. And that's how we are able to visualize the class separation, right? So in a way, we can say that, hear me out very carefully, what I'm about to say. We can say that glucose is a good predictor of diabetes. So by looking at this diagram, we can say, because the classes are well separated, the diabetes and not diabetes classes are very well separated, we can say that glucose is a very good predictor of diabetes status. If I know that the glucose level in the person is high, I am fairly confident that the person is diabetic. And if I know that the glucose level in the person is low, I can be fairly confident the person is not diabetic. So the glucose level in the bloodstream is a very good predictor of diabetes status. And this is very similar to the idea of correlation coefficient that we talked about yesterday. So in regression problems, we use correlations. So you remember the advertising data set we did, even today, the concrete data we did. Advertising yesterday, we saw that TV and sales had a very strong correlation. So it was like saying that, okay, TV is a good predictor of sales, right? Similarly here, when we are solving the classification problem, we will look at this data. We will do the initial exploratory analysis, what we are doing now. We are creating some plots. We're trying to understand our data better. And we can say that, yes, indeed, glucose is a very good predictor of diabetes status because the classes are very well separated. If I know the glucose level in the bloodstream, I am fairly confident that, yes, the person has diabetic. If the glucose level is more, the person is most likely diabetic. And if the glucose level is less, the person is not diabetic. So the glucose level in the bloodstream is a very good predictor of diabetes status. The more the glucose level, higher the probability of diabetes. Lower the glucose level, uh, lower the probability of diabetes. Okay. The same applies for some other features. I think if you see, there's another feature called body mass index. It's not as prominent, but you can still see the orange part is a little separated. Can you see? If I try to separate it out a little, the blue part is kind of this way, and which makes sense, no? Which makes sense that people with higher BMI are typically more prone to diabetes. I mean, it's like generally diseases. If you have a high body mass index, and it's like maybe it's more prone to obesity probably. High BMI is not a good thing, right? So if you have a higher body mass index, then maybe that is more prone to diabetes. Okay, so maybe it makes sense, and also to some extent age as well. If you see the last feature, age, uh, it is overlapping. It's not a very clear separation, but you are able to kind of see some semblance of separation. Maybe people with higher age, uh, like if you draw the distribution plots here, the average age for diabetic people is somewhere here, and the average age for not diabetic people is somewhere here. So you can see very clearly that there's a very clear separation that we can see between the classes. So if you're older, you're more likely to be diabetic, and if you are not that old, if your age is lesser, then you're less likely to be diabetic. Okay, so very good takeaways. We are able to, like, we just now studied what is classification. Classification is where you are trying to separate the classes. Remember, we are trying to find a model or a decision boundary that separates the classes, and here we are able to get a very nice pictorial understanding of how to identify good quality features. Okay, so this is a very good application of how pair plots are used in practice. Okay, so you can visually make out that, okay, some features are seemingly important, but some features are not important. Like, for example, blood pressure. Look at this feature called blood pressure. Okay, so if you look at this, the blood pressure feature, very interesting. The blood pressure is not a good feature. This is a pressure feature. Can you see? So if your pressure is high or your blood pressure is low, blood pressure usually has nothing to do with diabetic status. Okay, because pressure is dependent on other factors. If your pressure is high or if your blood pressure is low, the person may be diabetic, may not be diabetic. You're not able to see a very good separation between the classes. So these are bad features. If you eventually want to build a classification model, your objective should be to drop these kinds of features. You should actually drop these kinds of features like blood pressure and all this, or maybe even skin thickness. These kinds of features you will drop, but you want to take these kinds of features, feature selection. Okay, so all this is part of data pre-processing. So we talked quite a bit about data pre-processing, ideas of data pre. All this is ultimately part of data pre-processing. So you'll go and uh, identify good quality features, add new features like what we did for the New York City problem, taxi problem, uh, select important features. Part of what we did yesterday, we took TV, radio, we ignored the newspaper feature, the correlations were low, remember? And part of what we are doing now. So you can see very clearly glucose is good, it's a good feature, but the pressure and skin is not a good feature. So we don't want to include these features in our analysis. If we do that, then the model will not be good. The models that we end up building using these features will not be good. Okay, so we need to remove the noise and other things like skewness, encoding, scaling, all of these are pre-processing techniques. So you build the baseline model and try all these different things. So now try to add features, remove features, select the top features, scale the features, transform the features, remove the skew, remove the outliers, encode the features, convert your categorical values to numbers, and try to build different models. And by the time you complete your machine learning experiments, you would have built hundreds of models. Okay, believe it or not, you would have built thousands of models. What if I say you would have built tens of thousands of models? So by doing different experiments, you would have built tens of thousands of models before your final model makes it to production. POC is easy, but these are the experimentation parts that actually take time. But I hope the idea is clear. What is it? Now, obviously, it's very hard to visually make out what's going on. It's not practical to look at a diagram and say, hey, I think I see a good separation, because it's not practical. Uh, so what is the quantitative way to do it? There are a couple of approaches. We use some statistical techniques like p-values, which I don't want to get into right now, but it's not very used also. But p-values are one way to do it. The other way to do it, other more practical technique that is followed is this thing called feature importance. So we use something called feature importance to basically identify how important a feature is. So you can use something called a feature importance. And you see, I have listed out my features right now. And with respect to that, you can see that, okay, this feature is the most important. Okay, so the concept we have understood. How do we implement it? It is implemented using something called feature importance. So feature importance is something that will give you a mathematical value. It will tell you something about what is the importance of the feature. Again, this is calculated in a very different way. Some of you who know decision trees, who know random forests can relate to it. I think you guys know that there are entropies and all these things, how this is calculated. So that is a different conversation. Don't worry about that. This is the application. Next time you get any data set, what you can do is you can straight away compute a feature importance, and that feature importance will tell you how important is that feature in predicting the outcome. Okay, so it is kind of giving you the correlation between X and Y. Think of it that way. It is kind of giving you the correlation. So all these values will add up to 100%. So if you add up all these numbers, they will add up to 100%. Okay, and you're trying to identify which are the top features. So out of all these features that we are seeing on the screen, which are the top features? Which are the features which are having the highest correlations or the highest importance. And you can clearly see, very much in line with what we covered, you can clearly see that the top features are plasma. Plasma is the best feature because we saw the best separation here, right? Then we have something called body mass index, BMI. This is the third last feature. And then we have something called age.